What if I told you that scientists can only explain 5% of the entire universe? The rest, a staggering 95%, remains completely invisible to our instruments and defies our most advanced theories of physics. In this documentary, we're exploring the bizarre reality of dark matter and dark energy, cosmic components that shape our universe but remain utterly mysterious. Like trying to understand an entire ocean by examining a single drop of water, our current knowledge barely scratches the surface. We'll journey through cutting-edge discoveries and mind-bending theories that challenge our fundamental understanding of reality itself. The answers might be stranger than we ever imagined. The missing 95%. What if everything you can see in the night sky, all the stars, planets, and galaxies, makes up just 5% of what's actually out there? That beautiful spiral galaxy you've seen in photos, the stars twinkling above your home, the planets in our solar system, and even the atoms that make up your body, all of it combined represents just a tiny fraction of the total universe. When astronomers first came to this realization in the late 20th century, it shook the foundations of physics. Imagine the entire universe as an ocean. Everything we can see and detect directly, every star, planet, and galaxy, would amount to just a small cup of water from that ocean. The rest remains completely invisible to our instruments, detectable only through its gravitational effects. This wasn't a conclusion scientists reached lightly. The story begins with astronomers attempting to weigh the universe. They needed to determine how much matter exists in total, which turns out to be surprisingly difficult when you're dealing with something as vast as the cosmos. Scientists developed multiple independent methods to measure cosmic mass, and this is where things got strange. One approach involves studying how galaxies move within clusters. Galaxies aren't evenly distributed through space. They form groups in clusters held together by gravity. By measuring how fast these galaxies move, astronomers can calculate how much mass must be present to generate enough gravitational pull to keep everything together. It's similar to how we can determine Earth's mass by measuring the moon's orbit. Another method examines light from the early universe, the cosmic microwave background radiation. This ancient light carries imprints of how matter was distributed shortly after the Big Bang. By analyzing these patterns, scientists can determine how much matter existed then and track how it evolved into the universe we see today. A third technique involves gravitational lensing, when light from distant objects bends around massive structures like galaxy clusters. The amount of bending reveals the total mass causing the gravitational effect, similar to how magnifying glass bends light. What's remarkable is that all these different methods pointed to the same conclusion. There's far more mass in the universe than we can see. The calculations simply weren't adding up. The visible matter we can detect through telescopes, stars, gas clouds, planets, couldn't possibly generate enough gravitational force to explain what astronomers were observing. In the 1970s, astronomer Vera Rubin provided crucial evidence through her studies of galaxy rotation. She expected stars at the edges of galaxies to move more slowly than stars near the center, just like planets in our solar system. Mercury orbits much faster than Neptune. Instead, she found that stars throughout galaxies moved at roughly the same speed regardless of their distance from the center. This shouldn't be possible according to our understanding of gravity, unless there was substantial invisible mass distributed throughout each galaxy, providing extra gravitational pull. This discrepancy appeared everywhere astronomers looked, from small dwarf galaxies to enormous galaxy clusters. Something massive was missing from the equations. The same problem appeared when scientists studied the overall expansion of the universe. In the 1990s, astronomers discovered that the universe is accelerating in its expansion. This required some form of energy pushing everything apart, something completely different from the invisible mass holding galaxies together. Through decades of observations and calculations, scientists have now determined the universe's composition with remarkable precision. Ordinary matter, everything we can see and interact with, makes up just 5% of the cosmos. About 27% consists of dark matter, an invisible substance that interacts with normal matter only through gravity. The remaining 68%, the largest portion, is dark energy, a mysterious force driving the accelerating expansion of the universe. Dark matter doesn't emit, absorb, or reflect light, which makes it incredibly difficult to study. It doesn't interact with electromagnetic forces, yet it clumps together around galaxies in massive halos.
Without dark matter, galaxies,
they fly apart. They simply don't have enough visible mass to generate the gravitational force needed to hold themselves together. Scientists have proposed various candidates for what dark matter might be, from exotic subatomic particles to primordial black holes formed shortly after the Big Bang. Some have even suggested modifying our theories of gravity rather than introducing new invisible substances. Despite decades of searching with increasingly sophisticated detectors, we haven't directly observed a single dark matter particle. Dark energy presents an even greater puzzle. Unlike dark matter, which clusters around galaxies, dark energy appears uniformly throughout space. Its effects become more noticeable over vast cosmic distances. Some theories suggest dark energy might be an intrinsic property of space itself, that empty space contains inherent energy that drives expansion. Others propose more exotic explanations involving extra dimensions or modifications to Einstein's theory of gravity. The bizarre reality is that after centuries of astronomical observations and physics breakthroughs, scientists can only explain about 5% of the entire universe. We're like people trying to understand an iceberg by studying only the tiny portion visible above water. Understanding dark matter and dark energy could revolutionize physics, potentially leading to new technologies and a deeper understanding of how the universe began and how it might end. These invisible components have shaped the evolution of the cosmos from the earliest moments after the Big Bang, guiding the formation of galaxies and determining the ultimate fate of the universe. So what could possibly make up this missing cosmic mass? To answer that question, we need to examine one of the strangest discoveries in modern astronomy, the bizarre way galaxies rotate, seemingly breaking the fundamental laws of physics as we understand them. Galaxies that break physics. Why do galaxies spin as if they're breaking the fundamental laws of physics? According to everything we know about gravity and motion, galaxies shouldn't be able to rotate the way they do. Yet every galaxy we've examined reveals the same impossible pattern, a cosmic mystery that points to something massive hiding in plain sight. Let's start with how galaxy rotation should work according to Newton's laws of physics. Think about our own solar system. Mercury, the closest planet to the Sun, zips around its orbit at about 30 miles per second. Earth moves at a more modest 18 miles per second, and distant Neptune creeps along at just 3 miles per second. This pattern makes perfect sense. Objects farther from the center experience less gravitational pull and therefore move more slowly. This relationship is so reliable that we can use it to calculate the Sun's mass with remarkable precision. Galaxies should follow this same principle. Stars near the center of a galaxy should orbit rapidly around the galactic core, while stars at the outer edges should move much more slowly. Like dancers in a cosmic ballet, the performers closest to the center should twirl with dizzying speed, while those at the periphery should move in slower, more majestic arcs. If we graph the speed of stars versus their distance from the galactic center, we'd expect to see a clear downward curve, fast movement near the center, gradually decreasing as we move outward. This prediction comes directly from Newton's laws of gravity, which have been thoroughly tested and verified for centuries. But in the 1970s, astronomer Vera Rubin made a discovery that shocked the scientific community. Using a sophisticated spectrograph at the Kitt Peak National Observatory, Rubin studied the Andromeda Galaxy, our nearest large galactic neighbor. She measured how fast stars were moving at different distances from the galactic center by analyzing subtle shifts in their light spectrum, a technique called Doppler shifting. Stars moving toward us have their light compressed to slightly bluer wavelengths, while stars moving away have their light stretched to redder wavelengths. The amount of shift reveals the star's speed. What Rubin found defied all expectations. Stars at the outer edges of Andromeda were moving just as fast as stars near the center, sometimes even faster. This flat rotation curve appeared in galaxy after galaxy she studied. According to the visible mass of these galaxies, the outer stars should be moving much more slowly. Instead, they were whirling around at speeds that should literally fling them off into space. The conclusion was inescapable. Rubin later wrote in her notes, "The stars in the outer regions of galaxies were being influenced by matter we couldn't see." This revelation stunned astronomers, creating an immediate crisis in the field. Either Newton's laws of gravity were wrong, an extreme possibility given their success in explaining almost everything else in the universe, or galaxies contain vast amounts of invisible mass, extending far beyond their visible boundaries. The problem wasn't confined to a few unusual galaxies. Further studies revealed that virtually every galaxy demonstrated this same rotation pattern. Scientists began calling this missing component dark matter because it doesn't emit, absorb, or reflect light. Calculations showed that for most galaxies, The visible matter of stars, gas clouds, dust accounts for only about 10 to 20% of the total mass needed to explain their rotation. The remaining 80 to 90% must be invisible dark matter. Our own Milky Way galaxy appears to be embedded in a dark matter halo that extends far beyond the visible disk of stars, containing 5 to 10 times more mass than all the stars combined. Computer models suggest that dark matter forms roughly spherical halos around galaxies, extending much farther than the visible portions. The density of dark matter appears highest near galactic centers and gradually decreases outward. This extended distribution explains why stars at the outer edges of galaxies move so quickly. They're experiencing gravitational pull from a vast cloud of invisible matter surrounding the galaxy. Dark matter appears to form the backbone of cosmic structure. Computer simulations of the early universe show that dark matter clumped together first after the Big Bang, creating gravitational wells that attracted normal matter. Visible galaxies essentially form within these pre-existing dark matter structures, like cities built along invisible rivers. Scientists have mapped dark matter using a technique called gravitational lensing. When light from distant galaxies passes near massive objects, its path bends slightly due to gravity. By measuring these subtle distortions, astronomers can create maps of foreground mass, including invisible dark matter. These maps reveal vast webs of dark matter with galaxies nested within these invisible structures. Detailed studies of colliding galaxy clusters provide further evidence. When clusters collide, the normal matter, mostly hot gas, smashes together and slows down, while the dark matter halos pass through each other without interacting. The famous bullet cluster observation in 2006 showed exactly this pattern, providing compelling direct evidence for dark matter's existence. The rotation curves of galaxies tell us something profound about our universe. The stars and galaxies we see are just the visible tips of much larger structures. Without dark matter, galaxies would fly apart. The stars move too fast to be held together by the gravity of visible matter alone. Something invisible is holding our universe together. What makes this mystery particularly intriguing is that we can measure the effects of dark matter with remarkable precision. We can map its distribution, calculate its amount, and observe how it shapes galaxies and clusters. Yet we still have no idea what this mysterious substance actually is. It surrounds us, shapes our galaxy, and outnumbers visible matter 5 to 1. It continues to evade direct detection despite decades of increasingly sophisticated experiments. The phantom substance. How can something make up 27% of the universe yet remain completely undetectable by all our instruments? This is the central paradox of dark matter, a substance that appears to be everywhere in the cosmos, yet nowhere to be found. It's like having an invisible guest at dinner who eats more than everyone else combined, but leaves no trace of their presence except for the missing food. Dark matter earned its name because it doesn't interact with light or electromagnetic forces, the primary ways we observe the universe. Stars shine, gas clouds emit radiation, black holes consume matter and release energy, but dark matter remains invisible. It neither emits, absorbs, nor reflects light, making it essentially invisible to our telescopes and detectors. As Nobel Prize-winning physicist Maria Spiro-Poulou once remarked, dark matter is the ultimate cosmic ghost. We know it's there from its gravitational fingerprints, but it refuses to show itself directly, challenging our fundamental understanding of physics. This creates a strange situation for astronomers. We can map dark matter's distribution with remarkable precision to its gravitational effects, yet we still have no idea what it actually is. Imagine being able to create detailed maps of ocean currents without ever knowing water exists. That's essentially the position scientists find themselves in with dark matter. What makes dark matter particularly unusual is how it interacts with the universe. Normal matter, the stuff that makes up stars, planets, and people, interacts through 4 fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Dark matter appears to interact only through gravity, ignoring the other 3 forces. This selective interaction makes conventional detection methods ineffective, like trying to find a person who doesn't talk, doesn't leave, footprints, and walks through walls. And the only way you know they exist is because occasionally objects move as if someone had bumped into them. Scientists have developed several theories about dark matter's composition, with the leading candidate being WIMPs, weakly interacting massive particles. These hypothetical particles would have mass, explaining dark matter's gravitational effects, but would interact only weakly with normal matter. They would be fundamentally different from the particles in the standard model of physics, which describes all known particles like electrons, protons, and neutrinos. WIMPs are appealing because they would naturally form in the right amounts during the early universe. Calculations suggest they would have been produced in quantities that match the amount of dark matter we observe today. These particles would be all around us, passing through Earth constantly, yet interacting so rarely with normal matter that they remain invisible to our detectors. But WIMPs aren't the only possibility. Another candidate is axions, extremely light particles originally proposed to solve a different problem in particle physics. Axions would be much lighter than WIMPs, but could exist in such enormous numbers that they would collectively contribute the mass we observe as dark matter. Under certain conditions, axions can convert to photons, which gives scientists a potential way to detect them. Some researchers propose sterile neutrinos as dark matter candidates. Regular neutrinos barely interact with normal matter. Trillions pass through your body every second without affect. Sterile neutrinos would interact even less, making them potential dark matter components. Primordial black holes, formed in the first moments after the Big Bang, represent another intriguing possibility. These ancient black holes could range from microscopic to planet-sized and would interact only through gravity, matching dark matter's observed properties. Recent gravitational wave detections have renewed interest in this possibility. Dark matter forms an intricate cosmic web spanning the entire observable universe. This web consists of dense filaments and nodes with vast empty voids between them. Normal matter flows along these dark matter structures, like water following channels in the landscape. Computer simulations reveal that this cosmic web formed early in the universe's history. Dark matter began clumping together earlier than normal matter, creating a framework that would later guide the formation of galaxies. These simulations show something remarkable. If you map only the dark matter in the universe and add visible matter later, following the laws of physics, you naturally get a universe that looks just like our own. The galaxies form where dark matter density is highest, clustering in patterns that match our observations. Without dark matter, these simulations fail completely. The resulting universe looks nothing like the one we see. Dark matter acted as a cosmic scaffold, providing the structural framework upon which the visible universe was built. Galaxies form where dark matter filaments crossed or within dark matter halos, like cities built at the intersections of invisible highways. We can now map this cosmic web through techniques like weak gravitational lensing. When light from distant galaxies passes through the cosmic web, its path bends slightly due to dark matter's gravitational effects. By measuring these subtle distortions across millions of galaxies, astronomers can reconstruct dark matter's three-dimensional distribution. What makes this cosmic mystery so profound is the scale involved. Dark matter constitutes about 27% of the universe's total energy content, more than 5 times as much as all normal matter combined. It forms the backbone of cosmic structure and plays a crucial role in galaxy formation. Yet despite decades of searching with sophisticated experiments, not a single dark matter particle has been directly detected. This absence of direct detection has led some scientists to question whether dark matter exists at all. Maybe our understanding of gravity needs revision instead. But the evidence for dark matter has only grown stronger over time, with multiple independent observations pointing to the same conclusion. There's far more mass in the universe than we can see. The hunt for dark matter. What happens when the world's most sophisticated detection equipment keeps coming up empty-handed? This is the frustrating reality facing scientists hunting for dark matter. Despite building increasingly sensitive detectors, positioning them in the most remote locations on Earth, and spending decades searching, researchers have yet to conclusively detect a single dark matter particle. The search for dark matter represents one of the largest coordinated scientific efforts in history. Research teams across the globe have designed experiments costing hundreds of millions of dollars, yet this mysterious substance continues to evade direct detection. Finding something that barely interacts with normal matter requires extraordinary measures. One of the biggest challenges is filtering out false signals. Earth is constantly bombarded by cosmic rays, radiation, and particles that could be mistaken for dark matter interactions. To solve this problem, scientists have created the quietest detection environments possible. Many dark matter detectors operate deep underground, sometimes more than a mile beneath the surface. The rock above shields the detectors from cosmic rays. The Gran Sasso National Laboratory in Italy sits under a mountain with 1,400 meters of rock overhead, providing natural protection from unwanted signals. In these silent underground chambers, researchers wait patiently for the faintest whispers from the cosmos. The detectors run continuously for years. Scientists monitor data streams, hoping for that elusive signal that might finally reveal dark matter's presence. The silence grows more deafening with each passing year. Even underground, natural radioactivity creates noise in the detectors. Scientists address this by constructing massive tanks filled with ultra-pure materials like xenon, argon, or germanium crystals. These detection chambers are surrounded by carefully selected materials with minimal radioactive contamination. Some experiments use water shields, enormous tanks containing thousands of gallons of ultra-pure water to absorb stray radiation. The detection principles, while varied, share common elements. When a dark matter particle strikes an atom in the detector, it should produce measurable effects: a tiny flash of light, a few freed electrons, or a minute temperature increase. Sophisticated sensors capture these faint signals. The xenon experiment, buried deep under the Grand Sasso Mountain, contains thousands of kilograms of liquid xenon cooled to minus 95 degrees Celsius. Its sensors can detect even a single photon of light. The Lux Zeppelin experiment, nearly a mile underground in a former gold mine, holds 7 tons of liquid xenon surrounded by 70,000 gallons of water. Other detectors, like CDMS, use crystals cooled to nearly absolute zero temperature. Despite their remarkable sensitivity, these detectors remain silent. No experiment has produced a definitive dark matter detection confirmed by others. The Dama Libra experiment has detected intriguing seasonal variations for over 20 years, but other more sensitive experiments haven't confirmed these findings. Scientists pursue alternative approaches as well. Particle accelerators like the Large Hadron Collider try to create dark matter directly through high-energy collisions. If successful, these particles would appear as missing energy that went into the collision but disappeared from detectors. Years of operation have yielded no convincing evidence. Telescopes scan the skies for indirect signs. If dark matter particles collide in dense regions like the center of a galaxy, they might produce detectable gamma rays. The Ice Cube Neutrino Observatory in Antarctica searches for neutrinos that could be produced if dark matter accumulates in the sun and occasionally annihilates itself. The frustration is palpable among research teams. Each new null result sends them back to theoretical drawing boards. Yet there's also a strange satisfaction. Each failed detection narrows down possibilities. The search space gradually shrinks, pushing researchers toward more exotic theories. As conventional candidates are eliminated, scientists consider more unusual possibilities. Could dark matter exist in a hidden, parallel dimension? Might it consist of primordial black holes? Does our understanding of gravity itself need revision? The latest generation of detectors achieves sensitivity levels once thought impossible. The XENO-NNT experiment can detect interactions about 100 times rarer than its predecessor. These ultra-sensitive instruments peer deeper into the darkness than ever before. In hushed, sterile rooms deep beneath mountains, researchers continue their vigilant watch. Computers hum quietly, processing data. Occasional footsteps echo as scientists check equipment. The anticipation remains that at any moment, a signal might emerge from the background noise, finally revealing dark matter's identity. If these ultra-sensitive experiments still find nothing, physicists may need to reconsider fundamental assumptions. Perhaps dark matter interacts even more weakly than current theory suggests, or maybe it doesn't consist of particles at all. This ongoing failure to detect dark matter particles directly doesn't mean dark matter doesn't exist. The gravitational evidence remains overwhelming, from galaxy rotation curves to cosmic microwave background radiation patterns. What's unclear is the form this dark matter takes. After decades of increasingly sophisticated searches, the hunt continues with no end in sight. Each new experiment pushes the boundaries of detection technology, yet this mysterious substance remains stubbornly invisible. If direct detection keeps failing despite our best efforts, perhaps we need to reconsider our fundamental assumptions about what dark matter actually is, or whether our understanding of gravity itself needs revision. Something exists when we've never seen it directly. This is the central question at the heart of dark matter research. The answer lies in what scientists call convergent evidence, multiple independent lines of research all pointing to the same conclusion. While no single observation proves dark matter exists, the combined weight of evidence across different scales of the universe makes the case nearly irrefutable. Scientists face a stark choice: Either accept that an invisible substance makes up most of the matter in the universe, or reject fundamental theories of physics that have successfully explained countless observations for centuries. This scientific dilemma has pushed researchers to gather evidence from the largest scales of the cosmos down to the smallest structures we can observe. What secrets could the universe's oldest light reveal? The cosmic microwave background radiation, the faint glow discovered accidentally in 1964, represents leftover heat from about 380,000 years after the Big Bang. At that time, the universe had cooled enough for atoms to form, allowing light to travel freely through space for the first time. This ancient light has been traveling across the universe ever since, acting like a cosmic fingerprint of the early universe. In 2003, the WMAP satellite mapped this radiation, showing tiny temperature variations across the sky, just a few millionths of a degree. These variations form a specific pattern of spots and ripples containing detailed information about the early universe's composition, including dark matter content. The patterns in this radiation depend on the precise mixture of normal matter, dark matter, and energy present in the early universe. Computer models with about 5 times more dark matter than normal matter produce patterns matching the observations almost perfectly. Models without dark matter fail completely. The Planck satellite later refined these measurements, determining that dark matter makes up 26.8% of the universe's energy content, compared to just 4.9% for normal matter, with error margins under 1%. Have you ever wondered what happens when entire galaxy clusters collide? The Bullet Cluster, observed in 2006, provides a striking piece of evidence. During this cosmic collision, the normal matter, mostly hot gas, smashed together and slowed down, while the dark matter continued moving forward, creating a separation between the two types of matter, like oil separating from water after being shaken. Astronomers mapped the visible matter using X-ray telescopes, showing hot gas concentrated in the middle. They then mapped the total mass using gravitational lensing, revealing 2 distinct mass concentrations that had already moved past each other. This clear separation between visible matter and total mass provides powerful evidence for dark matter that's difficult to explain with modified gravity theories alone. How do galaxies form in the first place? Computer simulations show that without dark matter, galaxies would form much later and look quite different from what we observe. When dark matter is included, the simulations produce galaxy distributions remarkably similar to our actual universe. Dark matter began clumping together early in cosmic history, creating gravitational wells that attracted normal matter, like valleys collecting rainwater. Visible galaxies form within these pre-existing dark matter structures. Without dark matter's head start, normal matter alone couldn't have formed the complex galaxy arrangements we see today in the available time since the Big Bang. Can we map invisible matter across the cosmos? Gravitational lensing has become one of the most powerful tools for doing exactly that. When light from distant galaxies passes near massive objects, its path bends slightly due to gravity, an effect predicted by Einstein. By measuring these subtle distortions, astronomers create maps of foreground mass, including invisible dark matter. These surveys have revealed vast webs of dark matter stretching across cosmic distances, forming filaments and nodes where galaxies nestle within precisely as computer simulations predict. Around massive galaxy clusters, light from background galaxies can be stretched into arcs or complete rings, allowing precise calculations of how much mass must be present. Invariably, these calculations show far more mass than visible galaxies and gas can account for. The large-scale structure of the universe, how galaxies are distributed across space, fits together with dark matter predictions like pieces of an elaborate puzzle. Galaxy surveys have mapped hundreds of thousands of galaxies, revealing a vast cosmic web of filaments, walls, and voids. Simulations including dark matter naturally produce these same structures. Those without it fail to match observations. What makes these lines of evidence so compelling is their independence. Galaxy rotation curves, cosmic microwave. Background patterns, gravitational lensing, and structure studies use completely different techniques yet point to the same conclusion. About 85% of the universe's matter is invisible. Modern observations don't just tell us dark matter exists, they reveal its detailed distribution, quantity, and how it has shaped cosmic evolution from the Big Bang to the present day. The cosmic microwave background and other observations reveal the universe's hidden structure with such consistency that most astronomers consider dark matter's existence established beyond reasonable doubt. Some scientists have proposed modifying gravity theories rather than accepting invisible matter. These alternatives have had some success explaining individual observations like galaxy rotation curves, but struggle to account for the full range of evidence across different cosmic scales. As more precise observations accumulate, the case for dark matter grows stronger, while alternative theories face increasing challenges explaining our universe's complete picture. Alternative theories. What if we've been wrong about gravity for the past century? Since Einstein published his theory of general relativity in 1915, we've assumed that the same gravitational laws apply everywhere in the universe. But as evidence for dark matter has remained elusive despite decades of searching, some scientists are questioning whether we're looking at the problem backward. Maybe we're not missing mass. Maybe our understanding of gravity itself is incomplete. This possibility creates a profound dilemma for physics. Are we inventing an invisible substance that makes up most of the universe just to patch holes in our existing theories? Or should we instead modify theories that have successfully explained countless observations for over a century? This question has sparked one of the most interesting debates in modern science. The most prominent alternative to dark matter is modified Newtonian dynamics, or MON. First proposed by Israeli physicist Mordechai Milgram in 1983, MON suggests that Newton's laws of gravity work differently at extremely low accelerations found at galaxy edges. When gravitational acceleration falls below about 1/10,000,000th of Earth's surface gravity, the force becomes proportionally stronger than Newton's laws predict. This simple modification produces a remarkable result. It accurately predicts galaxy rotation curves without requiring dark matter. Stars at galaxy edges move faster than expected, not because of invisible matter, but because gravity itself behaves differently at these scales. As Einstein himself once remarked about quantum mechanics, God does not play dice with the universe. Perhaps similarly, gravity's true nature remains partially hidden from our current understanding. What gives MON credibility is its predictive power. It anticipated specific relationships between galaxy brightness and rotation speeds before observations confirmed them. These relationships, like the baryonic Tully-Fisher relation, emerge naturally from MON but require special explanations in dark matter models. Another compelling alternative comes from Dutch physicist Eric Verlin's emergent gravity theory. Verlin proposes that gravity isn't fundamental but emerges from quantum entanglement of space-time information. In this framework, the effects we attribute to dark matter actually stem from this emergent gravity behaving differently at large scales. Verlin's approach draws from string theory and black hole thermodynamics, suggesting space contains dark energy that interacts with normal matter to create effects mimicking dark matter. Other alternatives include tensor vector scalar gravity, TVIS, and conformal gravity. Each represents a different approach to the same idea, that our understanding of gravity needs revision rather than supplementation with invisible matter. Modified gravity theories have achieved notable successes. They explain galaxy rotation without additional assumptions about invisible matter and naturally account for relationships between visible matter and galactic properties. Philosophically, they follow Occam's razor by modifying existing laws rather than adding new universal components. However, these theories face significant challenges beyond galactic scales. While they work well for individual galaxies, they struggle with galaxy clusters, which show evidence for dark matter through multiple independent methods. The bullet cluster observation, where dark matter and normal matter separated during a collision, presents particular difficulties since gravitational effects clearly don't follow visible matter. Modified gravity theories also struggle to explain the precise patterns in cosmic microwave background radiation. Dark matter models predict these patterns accurately, while modified gravity approaches have difficulty matching all aspects of these observations. Similarly, cosmic structure formation simulations work naturally with dark matter but face challenges with modified gravity. The scientific community's hesitation to abandon general relativity makes sense. Einstein's theory has passed every experimental test for over a century, correctly predicting gravitational waves, black holes, and Mercury's precise orbit. This impressive track record makes scientists reluctant to significantly modify such a successful theory. This debate touches on philosophical questions about scientific advancement. Is it better to modify fundamental theories or add new components to the universe? History shows both approaches succeeding. Neptune's discovery explained Uranus's orbit without changing gravity laws. But Einstein developed a new gravity theory rather than proposing an unseen planet to explain Mercury's orbit. The dark matter debate mirrors this pattern. Are we in a Neptune situation, needing to find missing matter? or Mercury situation, requiring revised understanding of gravity? The answer remains unclear, with compelling arguments on both sides. Some scientists pursue a middle path, suggesting both approaches might contain truth. Perhaps some dark matter effects stem from modified gravity, while others come from actual particles. This hybrid approach could address strengths and weaknesses of both models. If modified gravity theories prove correct, it would trigger a physics revolution comparable to Einstein's overthrow of Newtonian mechanics. Conversely, detecting dark matter particles would confirm our basic gravity understanding while opening new windows into particle physics. What makes this debate fascinating is that both sides present solid evidence. Some scientists who studied this question for decades believe our understanding of gravity might be fundamentally wrong, offering radical alternatives that cannot be dismissed. As we wrestle with these competing explanations for galaxy rotation and cosmic structure, an even more mysterious force demands our attention, one that isn't holding things together, but driving them apart. Something is accelerating the universe's expansion, and understanding this dark energy presents an even greater challenge than either dark matter or modified gravity. These cosmic mysteries may ultimately be interconnected, pieces of a larger puzzle that our current theories have only begun to solve. The universe is accelerating expansion. Why is the universe not just expanding, but accelerating in its expansion, something that should be physically impossible? For decades, scientists held a straightforward view about the universe's future. After the initial explosion of the Big Bang, gravity would gradually slow the cosmic expansion, much like how Earth's gravity eventually pulls back a ball thrown into the air. The big question wasn't whether the expansion would slow down, but whether gravity would be strong enough to eventually reverse it completely, causing the universe to collapse back in a big crunch. This expectation made perfect sense. Gravity is an attractive force. It pulls masses together. Every object in the universe exerts a gravitational pull on every other object. With countless galaxies spread across the cosmos, their combined gravitational attraction should gradually break the expansion like cosmic friction. Astronomers were simply trying to measure how quickly this slowing was occurring. In the 1990s, two independent teams of astronomers set out to measure this deceleration rate. One group, the Supernova Cosmology Project, was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other, the High Z Supernova Search Team, was led by Brian Schmidt and Adam Rees. Both teams use Type A supernovae, stellar explosions so bright they can outshine entire galaxies, to measure distances to extremely distant galaxies and compare how fast they're moving away from us. These cosmic beacons serve as standard candles because they all explode with nearly identical brightness. Like knowing the wattage of a light bulb, astronomers can determine a supernova's distance by how dim it appears from Earth. The team spent years tracking these brilliant cosmic flashbulbs in galaxies billions of light years away, each explosion briefly illuminating the ancient cosmos. When the data started coming in, both teams noticed something profoundly unexpected. The most distant supernovae, those from billions of years in the past, were dimmer than they should have been. This meant these ancient explosions were farther away than predicted if gravity had been slowing the expansion. The universe wasn't behaving like a ball gradually losing momentum. It was acting like a rocket inexplicably gaining speed. The conclusion shattered cosmological orthodoxy. The expansion of the universe wasn't slowing down. It was speeding up. Imagine pushing a car downhill and expecting it to eventually roll to a stop, only to watch it mysteriously shift into higher gear and accelerate away on its own. At first, astronomers suspected a critical error. They meticulously rechecked their data, scrutinized their methods, and hunted for alternative explanations. Perhaps ancient supernovae differed from recent ones. Maybe cosmic dust was absorbing light, creating false readings. But after exhaustive analysis, both teams independently confirmed the same astonishing reality. The universe's expansion was indeed accelerating. This revolutionary discovery, announced in 1998, transformed our understanding of cosmic destiny so fundamentally that it earned Perlmutter, Schmidt, and Rees the 2011 Nobel Prize in Physics, recognition of how completely this finding rewrote our cosmic narrative. It introduced an entirely new mystery. What force could possibly overpower gravity across the entire universe? Scientists named this mysterious, repulsive force dark energy. The calculations revealed something astounding. Dark energy constitutes approximately 68% of the universe's total energy content, making it the dominant component of the cosmos, yet completely invisible and beyond our current understanding. Unlike dark matter, which clusters around galaxies, dark energy permeates space uniformly. More remarkably, dark energy appears to be a property of space itself. As the universe expands, creating more space, the amount of dark energy increases proportionally. Each cubic meter of empty space contains a tiny but fixed amount of dark energy that adds up to an enormous total force across the vastness of the cosmos. This characteristic creates a cosmic feedback loop with profound implications. The larger the universe gets, the stronger the acceleration becomes. The force driving galaxies apart intensifies as space stretches, ensuring ever faster expansion. Before this discovery, astronomers considered 3 possible cosmic fates: collapse in a big crunch, eternal but slowing expansion, or a perfect balance of forces. Dark energy introduced a 4th, more dramatic scenario: eternal acceleration, with galaxies retreating from each other at ever-increasing speeds. In this accelerating universe, distant galaxies will eventually recede faster than light due to expanding space itself. Eventually, galaxies beyond our local group will vanish from view, their light unable to cross the rapidly stretching void between us. Future astronomers will gaze into an apparently empty universe, all evidence of a broader cosmos having disappeared beyond an observable horizon. The discovery of cosmic acceleration raised profound questions that remain unanswered decades later. What exactly is dark energy? Why does it exist? Has its strength remained constant through cosmic history? Could it eventually become powerful enough to tear apart galaxies, stars, or even atoms in a cosmic Big Rip? Dark energy's existence has been confirmed by multiple independent lines of evidence, including detailed measurements of the cosmic microwave background and galaxy distribution patterns, all supporting the original supernova findings. The accelerating expansion stands as one of science's most significant and baffling discoveries. It reveals that something intrinsic to empty space itself is driving the universe apart against gravity's pull. What force could possibly accelerate the entire universe? This question leads us to examine the strange properties of empty space, which might not be so empty after all. The energy of empty space. Could empty space itself contain enough energy to tear apart the cosmos? This question sounds absurd at first. How could emptiness contain energy? Yet this is exactly what dark energy suggests, that the vacuum of space isn't truly empty but possesses an intrinsic energy that pushes the universe apart. Dark energy represents one of the strangest concepts in modern physics. Unlike dark matter, which behaves like invisible particles clustering around galaxies, dark energy appears to be a property of space itself. Every cubic meter of seemingly empty vacuum contains a tiny amount of energy, an energy that doesn't dilute as space expands. This concept challenges our intuitive understanding of emptiness and energy. Dark energy fundamentally changes how we view cosmic expansion. As the universe expands, it creates more space. Since dark energy is a property of space itself, more space means more dark energy. This creates a feedback loop. Expansion creates more dark energy, which accelerates expansion further. Think of it like a savings account that grows not just with interest, but also automatically receives more deposits as it grows. The balance accelerates over time. Unlike matter or radiation, which become more diffuse in an expanding universe, dark energy maintains constant density throughout cosmic expansion. The leading explanation for dark energy connects to a concept Einstein himself proposed and later rejected. In 1917, Einstein added a term called the cosmological constant to his equations of general relativity to create a static universe, since scientists then believed the universe was neither expanding nor contracting. When Edwin Hubble discovered the expanding universe, Einstein abandoned this constant, reportedly calling it his greatest blunder. Ironically, a version of this cosmological constant has returned as the simplest explanation for dark energy. In modern terms, it represents the energy density of empty space, vacuum energy. This vacuum energy creates a repulsive gravitational affect, pushing space apart rather than pulling it together. Einstein's equations allow for this possibility, showing that energy, even in the vacuum, can affect space-time's curvature. Where might this vacuum energy come from? According to quantum field theory, empty space resembles a simmering pot where energy bubbles constantly form and pop. At the quantum level, virtual particles appear and disappear too quickly to be directly observed, though their effects have been measured in laboratories. These quantum fluctuations contribute energy to empty space, potentially explaining dark energy. However, this explanation creates a massive problem. When physicists calculate how much vacuum energy should exist based on quantum theory, they get a value wrong by 120 orders of magnitude, a factor of 1 followed by 120 zeros. This represents the largest discrepancy between prediction and observation in scientific history. If quantum vacuum energy were really that strong, the universe would have torn itself apart instantly after the Big Bang. This huge mismatch has led physicists to search for alternatives. One possibility is that some unknown mechanism cancels out most of the enormous vacuum energy predicted by quantum theory, leaving just a tiny remainder we observe as dark energy. But this would require extraordinarily precise cancellation, a level of fine-tuning that many scientists find suspicious. Another alternative is quintessence, a dynamic field that permeates space, similar to the Higgs field that gives particles mass. Unlike the cosmological constant, quintessence can change in strength over time and might vary across space. This could explain why dark energy appears weaker than quantum theory predicts. Perhaps it was stronger in the past or would become stronger in the future. Some theories suggest dark energy might be leaking in from other dimensions beyond the 3 spatial dimensions we experience. Various string theory models allow for such possibilities, though testing these ideas remains extremely challenging. Whatever dark energy is, its long-term effects will be profound. If it maintains its current strength, the universe's expansion will continue accelerating. Over billions of years, galaxies outside our local group will recede faster than light, making them permanently unobservable. Their light will never reach us because space expands faster than light travels through it. This leads to cosmic isolation. Eventually, civilizations in any galaxy would look out at an apparently empty universe, with all other galaxies having disappeared beyond an observable horizon. The only galaxies visible would be those bound together by gravity into local groups, island universes alone in a vast expanding void. The ultimate fate of a dark energy-dominated universe depends on whether its strength remains constant or changes. If it maintains its current value, the universe faces a big freeze or heat death. Stars will burn out, galaxies will exhaust their gas for forming new stars, and the universe will grow increasingly cold and empty as everything spreads apart. A more dramatic possibility occurs if dark energy strengthens over time. In this big rip scenario, the accelerating expansion eventually overcomes not just the attraction between galaxies, but also the forces holding galaxies, solar systems, planets, and atoms together. The universe literally tears itself apart. The discovery that empty space contains energy capable of driving cosmic acceleration stands as one of the most profound scientific insights of our time. It suggests that emptiness itself has physical properties that shape the largest scales of the universe. Dark energy appears to be a fundamental property of empty space, growing in total strength as the universe expands simply because there's more space. This mysterious energy, making up 68% of the cosmos, remains largely unexplained more than 2 decades after its discovery. Its existence raises profound questions about the nature of space energy and the fundamental structure of reality. Dark matter and dark energy puzzles completely rewrites our understanding of reality. These cosmic mysteries touch on fundamental questions about the nature of existence itself. We're missing essential pieces of how reality works. Consider what's at stake. 95% of our universe consists of substances we can't directly detect or explain. Imagine exploring a continent where you can only see 5% of what's actually there. This is our current situation with the cosmos. We build impressive theories explaining the visible universe, but these theories account for just a tiny fraction of what exists. The quest to understand dark matter and dark energy could trigger a revolution in physics comparable to Einstein's theories of relativity or the development of quantum mechanics. Both of those earlier revolutions transformed our understanding of reality. Before relativity, we thought space and time were fixed and absolute. Einstein showed they're actually flexible, interconnected aspects of a single space-time fabric that can stretch, compress, and even curve in the presence of mass. Before quantum mechanics, we thought the world operated like a precise clockwork machine. Quantum theory revealed a strange reality where particles exist in multiple states simultaneously and can influence each other instantly across vast distances. The dark universe might force a similar conceptual leap. When scientists identify what dark matter actually is, it will likely reveal an entirely new class of particles or fields beyond the standard model of physics, the theory that currently explains all known particles and forces except gravity. The standard model has correctly predicted the existence of particles like the Higgs boson before they were discovered, but it can't explain dark matter. New particles would mean new forces or interactions we haven't detected yet. These could be subtle variations of forces we already know, or entirely new fundamental interactions. Discovering the nature of dark matter would expand our understanding of the basic building blocks of reality. It might reveal that the universe contains entire hidden sectors, parallel systems of particles and forces that interact with our visible world only through gravity. Dark energy presents an even more profound puzzle because it appears to be a property of empty space itself. Understanding it might finally help resolve the biggest conflict in modern physics, the incompatibility between general relativity and quantum mechanics. These two foundational theories contradict each other in certain situations, such as inside black holes or during the first moments of the Big Bang. Many physicists believe that a quantum theory of gravity would finally explain dark energy. Such a unified theory might reveal that what we perceive as empty space contains complex quantum structures or connections to extra dimensions. String theory, loop quantum gravity, and other approaches attempt such unification, but none has been definitively proven. Dark energy might provide the crucial clue needed to complete this theoretical puzzle. Beyond theoretical implications, solving these mysteries could lead to remarkable technological applications. Throughout history, fundamental discoveries in physics have enabled revolutionary technologies. Maxwell's equations describing electromagnetism led to radio and modern telecommunications. Quantum mechanics enabled transistors, lasers, and computers. What might we develop if we understood dark energy, a force powerful enough to accelerate the expansion of the entire universe? Perhaps new energy sources that tap into the vacuum energy of space itself. Such technology would represent the ultimate renewable energy, harvesting power from the fabric of space-time. Similarly, understanding dark matter might reveal new ways to manipulate gravitational fields, potentially enabling advanced propulsion systems for space travel or methods for studying the internal structure of planets without drilling into them. These discoveries would transform our understanding of cosmic history and the universe's fate. The Lambda CDM model describes how the universe evolved from the Big Bang, but includes dark matter and dark energy as placeholder terms. Identifying their actual nature would fill crucial gaps in our cosmic story. Dark matter played a critical role in forming the first structures in the early universe. Better understanding its properties might reveal exactly how the first galaxies formed. Dark energy will determine the universe's ultimate fate, whether it will expand forever, accelerating until galaxies are isolated, or whether its nature might change, potentially allowing expansion to reverse in the distant future. Perhaps most profoundly, solving these mysteries might reveal whether our universe is unique or part of a larger multiverse. Some theories suggest dark energy relates to the existence of other universes with different physical laws. If true, our entire conception of reality would need revision. We might discover our universe is just one bubble in a larger cosmic structure containing countless other universes. Are we approaching a paradigm shift in our understanding of physical reality? Many physicists think so. The standard theories that served science well throughout the 20th century have hit a wall with dark matter and dark energy. New approaches may require us to discard fundamental assumptions about how reality works. History suggests that when science confronts persistent mysteries, breakthrough insights often follow. The strange orbital behavior of Mercury puzzled astronomers until Einstein's relativity explained it. Today's cosmic mysteries may signal a similar conceptual breakthrough waiting to happen. What does it mean that we've detected something so fundamental yet so elusive? Humans, tiny beings on a small planet, have somehow discovered that 95% of the universe remains invisible to our instruments. This remarkable achievement speaks to the power of scientific inquiry. As we stand at this cosmic crossroads, we must ask, how might our understanding of ourselves and our place in the cosmos transform when we finally illuminate the dark universe? Cutting-edge research. What new experiments and technologies might finally solve the universe's biggest missing puzzle? Right now, a global army of scientists is deploying the most sophisticated detection equipment ever created in a high-stakes hunt for dark matter and dark energy. These experiments represent humanity's greatest effort to understand the 95% of the universe that remains invisible to our instruments. The search for dark matter has entered an exciting new phase. After decades of increasingly sensitive experiments coming up empty, scientists are expanding their approach beyond the traditional WIMP hypothesis. The XENONNT experiment in Italy's Gran Sasso Underground Laboratory represents the current state of the art in conventional dark matter searches. This detector contains over 8 tons of ultra-pure liquid xenon, making it about 3 times larger than its predecessor. Its remarkable ability to reject background radiation allows it to distinguish between genuine dark matter signals and constant bombardment from other particles like neutrons or gamma rays. While XENONNT looks for direct particle collisions, the ADMX experiment at the University of Washington hunts for axions, a completely different dark matter candidate. ADMX functions like a radio receiver tuned to detect frequencies where axions might convert into photons within a magnetic field. By exploring territory conventional detectors can't reach, ADMX could potentially find particles thousands of times lighter than previously searched for. Directional detectors represent another innovative approach. Experiments like DRIFT in the UK and DMTPC in the US aim to determine which direction dark matter particles come from. As Earth moves through the galaxy's dark matter halo, these detectors track tiny recoils of atoms struck by particles, preserving directional information. This approach could provide the smoking gun evidence needed to confirm a dark matter detection. Dark energy research requires entirely different methods. Since dark energy appears to be a property of space itself, scientists must map its effects across cosmic distances. Major space missions are transforming our understanding of cosmic acceleration. The European Space Agency's Euclid mission, launched in July 2023, is the first space telescope specifically designed to study dark energy. Euclid will measure shapes and redshifts of billions of galaxies spanning 10 billion years of cosmic history. Its revolutionary capacity to measure both expansion rates and cosmic structure growth provides 2 independent ways to track dark energy's influence. NASA's Nancy Grace Roman Space Telescope will launch later this decade with even more powerful capabilities. Its wide-field instrument will cover an area 100 times larger than Hubble with similar image quality, detecting subtle gravitational lensing effects across vast cosmic distances. Roman will determine whether dark energy strength has changed over time, a critical question for understanding its fundamental nature. Ground-based projects like the Dark Energy Spectroscopic Instrument, DESI, are making equally impressive strides. Operating since 2021, DESI will eventually measure precise 3-dimensional positions of 40 million galaxies using robotically positioned optical fibers. This will create the largest and most detailed 3D map of the universe ever made, revealing crucial constraints on dark energy models. These cutting-edge experiments harness revolutionary advances in quantum technology. Quantum sensors enable measurement at the very limits allowed by quantum mechanics. The Magus 100 experiment under construction at Fermilab uses atom interferometry, a technique treating atoms as waves, to search for ultralight dark matter and possibly gravitational waves. These methods can detect tiny forces that would have been undetectable just a decade ago. Quantum computing promises to revolutionize data analysis for these massive datasets. Where conventional computers struggle with complex simulations of dark matter distribution or extracting subtle signals from noisy data, quantum computers could perform these calculations exponentially faster, allowing scientists to test many more theoretical models. What makes modern research particularly promising is its interdisciplinary approach. The boundary between astronomy and particle physics has blurred. Particle accelerators probe matter's smallest scales, while astronomical observations reveal the universe's largest structures. Both provide complementary information about dark matter and dark energy. Early results from ongoing missions offer tantalizing clues. The Gaia space mission has created unprecedented maps of our Milky Way, revealing subtle irregularities in stellar motions that could indicate dark matter substructures. The South Pole Telescope has observed patterns in the cosmic microwave background, suggesting possible deviations from the simplest dark energy models. The international scientific community shares a profound hope that these tools will finally illuminate the cosmic shadows. Thousands of researchers across continents work tirelessly, united by the common goal of solving these fundamental mysteries. What if these breakthroughs are just the beginning of a complete transformation in our understanding of physical reality? These massive scientific efforts reveal something profound about human knowledge. We have developed the capacity to know what we don't know, to precisely measure our cosmic ignorance. This knowledge of our limitations represents a triumph of the scientific approach, driving us to develop ever more ingenious methods to probe the unknown. What might these cosmic mysteries ultimately tell us about science and human knowledge? Perhaps that our greatest discoveries often begin with our greatest puzzles. The greatest mysteries in science have always led to our most profound discoveries. Dark matter and dark energy aren't failures of scientific understanding. They're opportunities that could completely transform how we see reality. These mysteries push us to develop new technologies, new theories, and entirely new ways of thinking about the universe. What strikes me most is that humans, tiny beings on a small planet, have measured something we can't see or touch. We've glimpsed the cosmic unknown from our modest corner of existence. We stand at the threshold of discovery, poised to rethink not just our scientific models, but our very